We're going to go over section 8.8, and our objective will be to find the moduli of a complex number. So it's been a while since we've talked about a complex number, and moduli is going to be a new vocabulary word. So before we get started, let's look at our warm-up. It wants us to state the Pythagorean theorem. So hopefully we've got this already memorized, but a squared plus b squared equals c squared. And just as a side note, this theorem only works if we have a right triangle. So we'll keep that in mind. Number 2, a complex number is written a plus bi, where a is going to be our real number and the bi is our imaginary number. So any complex number is written of that form. Number 3, a vector, which takes us clear back to secondary 1, but a vector is a quantity that measures distance, so we can find an actual length of that, and magnitude. So last year we talked about and we found both of these. So remember, we represent a vector using what's called a directed line segment. So we have an arrow on it, kind of like a ray. It would have to start in one location and go in a direction. And we say a vector is in component form if it begins at the origin. So today's section, we're going to combine lots of things that we've done before: Pythagorean theorem, our imaginary numbers, this idea of vectors, and start getting us thinking about some of this honors trig. So let's look at below at some vocabulary. It says that the complex plane is where the horizontal axis represents the real component A, and the vertical axis represents the imaginary component bi of a complex number. So we've not worked on a complex plane before, but now we have complex numbers, so we should be able to start working with those. So as it says, our real component, or the A, is going to be that horizontal axis. So I'm going to label on this axis over here. This is going to be my real number, or that A value. And then on the vertical axis, we were going to have that imaginary axis. That's that vertical axis, which is our bi, that B term. Take off the I, just the B term, excuse me. So this is our complex plane, very similar to X and Y. And we should be able to graph and do all sorts of things on it. So we note, below that the rectangular form of a complex number, a plus bi, is written as a comma b, which is very similar to our x, y that we've dealt with before. So we'll put any real number on our real axis and any imaginary on that vertical axis. So very similar to x and y. To graph a point in the complex plane, we're going to graph A units horizontally and B units vertically, just like we would do if it was an XY. So let's go ahead and look at some things here. So let's go ahead and start at the origin. And let's say we go a distance A on that real axis, and then we go a distance vertically up to B. So this point has a location on our graph, and we can denote it with the ordered pair A comma B. Our next vocabulary says that the modulus, which is the plural form of moduli, which we saw up in our objective, the modulus of a complex number is defined as, so we notice that we have this Z with our absolute values around it. And it's technically in that vector notation, it looks like absolute values, but it's actually talking about magnitude or length. So we can find the length of any complex number if we're thinking about a vector in component form. So remember, we said in the warm-up, if a vector is in component form, it starts at the origin. So let's kind of adjust our picture here for a second. If I'm at the origin and I go a vector A, it has a length and it has a direction. right? A magnitude and a direction. And then go from that point, vector B also has a length and a magnitude direction. I could also go the shorter distance from my origin to my ending point AB. This is what's referring to as Z. And because every time a horizontal and a vertical vector would intersect, we'd get a right triangle. So essentially, we're just doing Pythagorean theorem to be able to find the magnitude of this vector. So that's what those vertical lines around the Z are representing, is that magnitude, trying to find that length. So we have vectors now that we can find their magnitude of using our our Pythagorean theorem. And we now know that this is going to be called a modulus. So for complex numbers, we'll call this a modulus, or if we find plural forms, we'd say moduli. So let's go ahead and practice a little bit of graphing. Example 1 says to write the following complex numbers in rectangular form. So that's that new A comma B. And then we'll graph them on the complex plane. So on my complex plane, I know I have real on that horizontal axis, and I have imaginary on that vertical axis. So all of these are in complex form currently. So to change these to rectangular, I have to be looking at the real versus the imaginary. And remember, these are always of the form A plus BI. So my real number will always be that A, which should be written first if it's in the correct form. So there's my A in my rectangular form. And my B would always be in front of my I, and we want to make sure we take the sign. So in this case, that's a -2. So my next one, same idea, my real number, comma, that coefficient in front of my I. C, my real, and my coefficient on I this time is -1. Be careful on that. And then we have a -5. And then we have a +3 coefficient there. And all of these now can be graphed because our real axis is A and our imaginary axis is B. So essentially, this is going to feel just like graphing anything else. Starting at the origin, I'm going to do problem A. I'm going to go 3 units on the real axis and down 2 units on the imaginary. Done. 4, 5. 4 units on the real axis, 5 on the imaginary. -2, -1, and -5, +3. So this is going to hopefully feel pretty easy, the graphing part. We just want to make sure we get them in the correct form. Let's go ahead and look at example 2, which is very similar. Again, the directions want us to write this in rectangular form and graph these on a complex plane. So again, I'm remembering that these are always, if they're in complex form, A plus BI, which means in my rectangular form, I need my real, comma, the coefficient on my imaginary. I'm not going to label my axes anymore. We know that we would go 3 on that positive real axis and then down 2. And then 4, 5. So again, we have that A plus BI. So 4, comma 5. And then we lastly would have, let's see, -2, comma -2. So from our origin, -2, -2. Let's go ahead and turn the page. And let's find the length of moduli. So when I'm looking at these problems now, I'm thinking they all were the hypotenuse of a right triangle. That's what I'm trying to find. So if it would be helpful to you, we could sketch a little bit. I know if I have Z, that would be the hypotenuse of that right triangle on the complex plane. And I have this complex number, which is essentially a vector, starting at that origin and going 3 units on the real axis and 4 on the imaginary. So that means I'd have a vector ending right there. So I can form a right triangle that would go over 3 units and went down 4 units. So Pythagorean theorem says I can find the length of my modulus. So I'm going to go ahead and use my notation here. The length of my modulus to find the magnitude of that vector. I'm going to take my 3 squared plus my b squared. Just be careful about simplifying. We'd end up with 9 right here, and we end up with 16. So that would give us a square root of 25, which is a 5. So the length of my modulus, that vector, would be 5 units. Let's do the same thing on b. Again, you could draw a graph. We know that this would be starting at the origin. We go over 2 units on the real axis and 3 units up on the imaginary. So there's that vector that we could create a right triangle with. So the length of my modulus, that vector, would be 2 squared plus 3 squared. So this is not going to be a whole number because we're going to end up with 4 and 9, which is 13. Normally, I would say when we're finding length of something, a decimal is a pretty good choice here. So let's go ahead and use our calculator and find the square root of 13. I should have put this in the directions, but let's just round to the nearest tenth. So 3.6. The length of our modulus would be about 3.6. Okay, problem C, I notice a change in notation here. My first 2 problems were given to me as complex numbers, but these last 2 problems are given to me in rectangular form. These are rectangular form, which is what we're used to seeing. It looks more like an ordered pair to us. So if I again was thinking about graphing, I know that I would go 3 on the positive axis there and down 6. So we can do the exact same thing. I can find the length of that modulus, 3 squared plus negative 6 squared. Let's see, that's going to be 9 and 36. So the square root of 45, which unfortunately is not a whole value. So I'm going to go the square root of 45 and get 6.7. Okay, let's look at one more. Again, this is in rectangular form. I'm not going to draw a graph this time. I know I'm finding the length of that modulus. And the length of the other 2 sides would have to be a 9 and a 12. So definitely a little bit bigger numbers here. I know this would be 81 and this is 144. So let me just double check. 81 plus 144. Oh, 225. Do we recognize 225? If not, use your square root button because the square root of 225 is 15. So nice. We ended up with the square root of 225, which ended up to be a whole number of 15 for us. All right, so today's assignment, we're going to practice graphing on this complex plane and going between these 2 forms of rectangular, and go ahead and self-assess, and good luck on your assignment.